of this video is the Handshaking Lemma, or also called the first theorem of graph theory. This theorem states that in any graph, the sum of the degrees of the vertices is equal to twice the number of edges. We could also briefly write that as the sum of the degrees of the vertices is equal to twice the number of edges. We're going to prove this theorem, but let's verify that it works for an example or two. So let's consider this graph G, and in this graph G, the sum of the degrees of the vertices is what we get when we add up the degree of A. The degree of A is 3 because A has 3 edges incident with it, plus the degree of B is 2, plus the degree of C is 3 as well, plus the degree of D is 2, plus the degree of F is 0. Now when we add up those values, we've got 6 plus 4, we have 10. And let's also look at how many edges are in the graph. So the number of edges in the graph is 1, 2, 3, 4, 5. There are 5 edges in the graph. So the cardinality of that set, the number of edges in that graph, is 5. And yes, it is true that 2 times 5, twice the number of edges, is equal to 10. So great. This graph claims to work for any graph, not just simple graphs, so it should also work when there's multiple edges or loops. Let's check this out with the graph H. So in H, the sum of the degrees of the vertices is the degree of x, that's 1, 2, 3, 4, plus the degree of y, that's 1, 2, 3, 4, 5, plus the degree of z, so that's 1, and then remember a loop contributes 2 to the degree, so 1 plus 2 is 3. So the sum of the degrees is 12. And now let's check the number of edges. So the number of edges in this graph is 1, 2, 3, 4, 5, 6. There are 6 edges in this graph. And so let's verify the theorem. The twice the number of edges is 2 times 6, which is 12. And yes, that is equal to the sum of the degrees of the vertices. Great. So we've seen the theorem work in 2 examples, but let's show that it always works for every graph. So here's our proof. The degree of a vertex is the number of edges incident with it. So we know that each normal edge, each non-loop, is incident with 2 vertices, and a loop is incident with just 1 vertex, but it contributes 2 to the degree. So when we add up the vertex degrees, each edge gets counted twice. So for example, if y has degree 3, this edge was counted when incident with y, but it's also going to be counted again with whatever else it's incident with, and same deal for this edge. And so this edge gets counted twice, this edge gets counted twice, this edge gets counted twice. This edge also adds 2 to the degree because it is a loop. So adding the degrees of each of the vertices is going to count every edge twice. Is it going to be equal to twice the number of edges? And that's the end of our proof. So we can celebrate having finished a proof by doing a little square and saying that's the end of our proof. We could also write QED if we wanted, but either way, our proof is done. Okay, let's see one small application of this theorem. Suppose a graph has 3 vertices of degree 2 and 4 vertices of degree 3. How many edges must it have? So we could draw such a graph and then count the edges, but we could also use the theorem we've just proved. So the sum of the degrees of the vertices is, well, there are 3 vertices of degree 2. So I have a vertex of degree 2, another vertex of degree 2, a third vertex of degree 2, and there are 4 vertices of degree 3. So degree 3, degree 3, degree 3, degree 3. Notice I could have also just written that as 3 vertices each of degree 2 plus 4 vertices each of degree 3. But in any case, I've got 6 plus 12, I've got 18. So 18 is the sum of the degrees of the vertices, and I know that 2 times the number of edges is equal to the sum of the vertex degrees. So I can divide both sides of my equation by 2, and now I know that the number of edges in this graph must be 9. If we wish, we could verify that by drawing some graph with 3 vertices of degree 2 and 4 vertices of degree 3. There's different graphs you could draw. One would be this graph. So we could do 1, 2, 3, 4, 5, 6 vertices and make a cycle around them. So far, each of these vertices has degree 2, and then we could put one vertex in the middle and connect it to 3 of the vertices. So now we've got 1, 2, 3, 4 vertices of degree 3 and 1, 2, 3 vertices of degree 2. So there's one graph G that meets that criteria. Let's make another one. We could also make a disconnected graph that meets that criteria. So we could have a cycle with 3 vertices on it, and then also have a set of 4 vertices that are each connected to each other. 1, 2, 3, 4, 1, 2. And so now we also have another graph, H, that has the property that there are 3 vertices of degree 2 and 4 vertices of degree 3. And we can count in each situation and verify that there will be 9 edges in each of those graphs. Okay, let's look at a similar example. If a graph has 3 vertices of degree 2 and 5 vertices of degree 3, how many edges does it have? Okay, well, let's do the same thing. We're going to do the sum of the degrees of the vertices. And so there's 3 vertices of degree 2. That's 3 times 2, or plus there are 5 vertices of degree 3. So that's 5 vertices each of degree 3. Repeated addition is just multiplication. So, okay, that's the sum of the vertex degrees. Let's add those 2 values together. That's 6 plus 15. There should be a sum of 21. And so we can again use that formula. The sum of the degrees of the vertices is equal to twice the number of edges. So 2 times the number of edges is equal to 21. Again, we can divide both sides of the equation by 2. And so the number of edges is 21 divided by 2 is 10.5. Okay, is that an acceptable answer? No, it isn't. We cannot have half an edge. So there are no half edges allowed in a graph. What would a half edge be? I mean, in theory, it could be a vertex and nothing on the end, but we say that this is not allowed. And therefore, no such graph exists. You could try to draw it as much as you wanted. You could try to draw many such graphs, and you would never be able to. So that's kind of an interesting property. Let's see if we can generalize it. So what went wrong? The thing that went wrong was that we ended up having an odd number for the sum of the vertex degrees And when we divide an odd number by 2, we get a value that isn't an integer, a value that can't be a number of edges. So again, how did that happen? Okay, so here we've got an even number plus 5 times 3, that's an odd number. And anytime we add an even number plus an odd number, we get an odd number. And more specifically, anytime that we add some number, anytime that we add an odd number of odd numbers, the value will always end up being odd. So we've come across a corollary to our main theorem. A corollary is a result that follows immediately from some previous result. So in this case, we have figured out that a graph cannot have an odd number of vertices of odd degree. Why is that the case? That's because if we add up the degrees of the vertices, and there's an odd number of vertices of odd degree, that odd number of vertices of odd degree, if we add those up, we will get an odd value, plus all the other vertex degrees would be even, and if we add up a bunch of even values, we will just get an even value. Anytime we add an odd number plus an even number, like for example, the number 5 plus the number 2, we get an odd number. And so if the sum of the vertex degrees is odd, then we have 2 times the number of edges is equal to an odd number. And so the number of edges is equal to an odd value divided by 2. By definition, an odd value is not divisible by 2, so this is not an integer. However, we can't have a non-integer number of edges, and this is a contradiction. So we have just done a proof by contradiction that a graph cannot have an odd number of vertices of odd degree. And again, we finished that proof, a little square or a little QED.